Hello, everyone. I'll be talking about measures of position, and for assessment of learning, this would be the last statistical topic that I'm going to present in the class. But in the statistics class or in the research class, this is just one of the many statistical tools to be used under descriptive statistics. So again, this is all about measures of of position. Objectives: how to find the first, second, and third quartiles of a data set, how to find the interquartile range of a data set, and how to represent data set graphically using a box and whisker plot. How to interpret other fractiles such as percentiles, and how to find percentiles for a specific data entry. Next, determine and interpret the standard score or the so-called z-score. When you encounter z, that represents the standard score or the z-score. So first, we'll take up quartiles. Under quartiles, we'll be talking about fractiles in general. Fractiles are numbers that partition, divide, and order data into equal parts. So that's the overall term, fractiles. Are numbers that partition or divide unordered data, meaning data arranged from lowest to the highest or highest to the lowest one. Remember, in the computation of median, we make use of ordered data, wherein we say ordered data, these are data that are arranged from lowest to the highest or highest to the lowest. Quartiles approximately divide unordered data into four equal parts. So quartiles divide a given set of data into equal parts, where the data are actually arranged from highest to the lowest one or from the lowest to the highest one. In general, this is what we call ordered data. So we have the first quartile labeled as Q1, second quartile Q2, third quartile Q3, and then the highest one is quartile number 4. So for first quartile, about one quartile of the data fall on or below Q1. Second quartile or Q2, about one half of the data fall or below Q2. And then third quartile or Q3, about three quarters or that's 75%. No, each quarter is 25%. So if we have three quarters, so a total of 75%. So about three quarters or about 75% of the data fall on or below the value of Q3. So finding quartiles. Each year in the US, automobile commuters waste fuel due to traffic congestion. The amounts in gallons per year of fuel wasted by commuters in the 15 largest US urban areas are listed. Find the first, second, and third quartiles of the data set. What do you observe? So these data are taken from based on 2015 Urban Mobility Scorecard. So that's the source, no? Based on the 2015 Urban Mobility Scorecard. So here are the data: 20, 30, 29, 22, 25, 29, 25, 24, 35, 23, 25, 11, 33, 28, and 35. So you notice that the given data are not ordered, not arranged from lowest to the highest one or the opposite one, highest to the lowest one. So we need to order the data. So ordering the data would have 11, 20, 22, 23, 24, 25, 25, 25, 28, 29, 29, 30, 33, 35, then 35. So we are going to look at first into how many data are in the set. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we're going to get first Q2. And you have to remember that Q2 or quartile number 2 is equal to the median. And recall the calculation of median. If the total number of data in the set is odd, so we have plus 1. So since 15 is odd, so we have 15 plus 1, then divided by 2. So 15 plus 1 divided by 2, so we have 16 divided by 2, or that is equivalent to 8. So count 8 starting from the the lowest one. 1, 2, 3, 4, 5, 6, 7, 8. So number 8 is number 25. We can count 8 also starting from the highest one. So we have 1, 2, 3, 4, 5, 6, 7, 8. So our Q2 is equal to 25. So Q2 is actually the same to the median. So if you're going to interpret the Q2 or the median, that's 50% of the data are having values equal to 25 or maybe less than 25. Or it can be quartile number 2, or the second quartile means that 50% of the data are having values equal to 25 or less than 25. And it is mentioned in here about one half of the data fall on or below Q sub 2, and that is equivalent to the value of the median as part of the definition. So it is mentioned in here in about one quarter of the large urban areas, so auto commuters waste 23 gallons of fuel or less. So if we're going to look at this one, so this is Q2, and we have Q2 also, that is half below Q2, and this is what greater than Q2, and this one equal to Q2. So if you're going to look at into quartiles, divide the data into 4 equal parts. So we need to have a division of this into 4 equal parts. So we have 1, 2, 3, 4, 5, 6, 7. 7. So 7 is actually odd. So if we're going to get the middle part or the median of these numbers, so we have 7 plus 1, 8 divided by 2. Why plus 1? Because the total number of data is odd. So we have 1, 2, 3, 4, 5, 6, 7. So 7 plus 1, 8 divided by 2. So count the 4, starting from the highest, 1, 2, 3. We have 1, 2, 3, 4. No? So we have here 1, 2, 3. Then supposedly 4. We have 1, 2, 3. Then we have 4 also. So if you look at this, we have 23. No? Weighs 23 gallons. So we have the location of Q1. It's in here. No? So we have Q1. So all in all, actually, if you're going to look up into these values, including the median, 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2, so 4. 1, 2, 3, 4. Starting from the highest one, we have 1, 2, 1, 2, 3, then 4. So we have 23. No? 1, 2, 3, 4. We have 1, 2, 3, 4. That's why we have a mention in here. We have about one quarter of the large urban areas, auto commuters waste 23 gallons of fuel or less. So it could be less than 23 or maybe equal to 23 in terms of the requirement for number 1. According to number, find the first, second, and third quartiles of the data set. So looking into the other one, so we have here 1, 2, 3, 4. We have 1, 2, 3, 4. So we have 30 also in here. Why? Because we have the other half. So we can get the median of the other half. So that's actually 30. 1, 2, 3, 4. We have 1, 2, 3, 4. So our third quartile or quartile number 3 is equal to this one. So we have now about one half of weighs 25 gallons or less, and about 3/4 weighs 30 gallons or less. So we have 30 gallons. So when you say about 3/4, it's all about 75%. 1/4 is equal to 25%. So 3/4. So 75%. So about 75% weighs 30 gallons or less. So it can be 30 gallons or maybe less than 30 gallons. So remember that we start from the very lowest value up to the highest value. So take note of that interpretation. So about one quarter, or that's 25% of that data in urban areas, auto commuters waste 23 gallons of fuel or less. So 23 or less than 23 gallons. And then about one half, that's 50%. No? Waste 25 gallons or less, or 25 gallons or less than 25 gallons. And about three quarters, that's 75%. Why 75%? Because each quarter is equal to 25%. So take note of the exact analysis and interpretation of the data. Now, the quartiles can be generated also using technology. No? So later I'll be introducing about technology, how to calculate that one using technology. So using technology to find quartiles. So the tuition costs in thousands of dollars for 25 liberal arts colleges are listed. Use technology to find the first, second, and third quartiles. So what do you observe? So we have 50, 52, 51, 49, 52, 51, 25, 41, 47, 36, 30, 44, 40, 35, 40, 45, 34, 33, 23, 34, 37, 16, 18, 18, then 35. So all of this will be loaded to the software. It can be Minitab, it can be TI-84, or even Microsoft Excel, and the SPSS. No? The meaning of SPSS is Statistical Package for the Social Sciences. So you notice that from Minitab, you are given directly this kind of table. So automatically this table is generated by Minitab. If you're going to use TI-84, this is actually generated also. StatCrunch as a software, this can be generated also directly. And then if you're going to use SPSS, then those values can be generated automatically also. I'll introduce that one in another video when we talk about the software, no, to calculate the quartiles. So let's go to interquartile range. Interquartile range is a measure of variation that gives the range of the middle portion about half of the data. That's the middle 50%. It's the middle 50%. The difference between the third and first quartile. So interquartile or IQR is equal to Q3 minus Q1. So from Q1 up to Q3, we classify that one as the middle 50%. Interquartile range. So using the interquartile range, identify outliers. So first quartile and third quartiles of the data set. Find the interquartile range, IQR, Q3 minus Q1. Multiply IQR by 1.5. That's 1.5 times IQR. So 1.5 is constant in there. Subtract 1.5 IQR from Q1. Any data entry less than Q1 minus 1.5 QR is an outlier. Add 1.5 times IQR to Q3. Any data entry greater than Q3 plus 1.5 IQR is an outlier. Remember, in the video about measures of central tendency, I talk about outliers. So I hope you remember about the definition of outlier. So outliers are actually very big values in comparison to the majority of the data, or it can be very small value in comparison to the majority of the data. So find the interquartile range. So find the interquartile range of the data set from the first example. Are there any outliers? So Q1 is 23, Q3 is 30. So the interquartile range is Q3 minus Q1. So 30 minus 23 is equal to 7. So to identify any outliers, we follow the formula. 1.5 times IQR is equal to 1.5 times 7. So 10.5. There is a data entry 11 that is less than Q1 time minus 1.5 times IQR. That's 23 minus 10.5, so 12.5. So any data entry less than 12.5 is an outlier. And in here, we have here, um, first note, no, we have 10.5, and then the other one is 12.5. So for Q3 plus 1.5 times IQR is equal to 30 plus 10.5. So we have 40.5. Any data entry greater than 40.5 is also an outlier. So 11 is an outlier. So if you look at the data in here, so you can find the data from the original one. Look at the data. So these are the data given in here. So let's look at the data. No, this is the data here. This is the data. 11, 20. We have 22, 23, up to 35. If you look at 11, this is actually a small value in comparison to the majority of the data. So we classify 11 as an outlier. So it is stated in here as part of the verification that 11 is an outlier. So in large urban areas, the amount of fuel wasted by auto commuters in the middle of the data set varies by at most 10.5 gallons. Notice that the outlier 11 does not affect the interquartile range. So next term is all about box and whisker plot. So box and whisker plot. So this one is part of exploratory data analysis tool. Highlights important features of dataset. And this would include the five-number summary. So five-number summary is very common in descriptive statistics. And what do you see in a five-number summary? You can find the minimum entry, the first quartile, the median, the third quartile, and the maximum entry. So these are the five numbers that you can find, no, in a five-number summary. You need to look at the minimum. You need to look at the maximum. You need to find the value of quartile number 1 or Q1, the value of quartile number 2 or the median, and quartile number 3 or Q3. So drawing a box and whisker plot. No? So find five-number summary of the data set. Construct a horizontal scale that spans the range of the data. Plot the five numbers above the horizontal scale. Draw a box above the horizontal scale from Q1 to Q3 and draw a vertical line in the box at Q2. Draw whiskers from the box to the minimum and maximum entries. So we look at the data in here. So we have this line. So we have to consider the minimum. We have to consider the maximum. And we have to consider Q2 and then Q1, the location of Q1, and then the location of Q3. So we have there whisker. It's actually this line from the minimum going to this point in the box, whisker. From this point of the box going to the maximum value, we classify that one as whisker. And once you label already Q1, Q2, and Q3, you are going to form a rectangular box. So this rectangular box colored by blue is what we call the box. And we have the whiskers. We have two, one going to the maximum value starting from the rightmost part of the box or the rectangle. And then from the minimum value going to the leftmost part of the rectangle or of the box is also another whisker. That's why we call it one as box and then whisker plot. So we have two whiskers. There's only one box and there are two whiskers. So take note, when you draw the box, it would not be that big. No? Just have an ideal one. Not so big nor so small box. But of course, the box, when you're going to have the rectangle, from one point to another point of the length of the box must contain Q1 and then Q3 and passing to Q2. Example, drawing a box and whisker plot. So we have minimum 11, Q1 is equal to 23, Q2 25, Q3 30, maximum is 35. And of course, you are going to have proper scaling of your x-axis or the number line. The scaling must be equal to each other. Like from 5 to 10, the distance must be the same to 10 to 15. And the distance from 15 to 20 must be the same to 25 to 30, must be the same to 30 to 35, must be the same to 35 to 40. Not in the case na one interval, the length is this one, another this one, then another one. So the lengths or the intervals of those different numbers found in the number line do not have equality. So no, no, no for that. So you have to use a ruler. You are going to use a scaling material or an instrument so that the distances between and among numbers are actually equal to each other. Why? Because if there is no equality on the distances between one number to another number on the number line or in the x-axis, then basically you could not get an appropriate graph or an exact graph. So locate 11, this location of 23, this the location of 25. This one is the location of 30, and this one is the location of 35. So connect 11 to 23, and then situate that you're able to have a box wherein the box would not be that big. Just connecting 23 to 30, have a box. Then label also Q2, that's 25. Then put also a line. So you notice that we have a line segment for 23, a line segment for 25, a line segment for 30, and then drawing the rectangle and the, or the box. Now we classify that one as the box, or we're saying that that's actually a rectangle. Then from 30 to 35, we classify this one as box. From 11, no, whisker. From 11 to 23, we classify that one as whisker. The colored blue geometric figure is what we call the box. So we classify this one as box and whisker plot. So there are two whiskers and there's only one box. So the box represents about half of the data, which are between 23 and 30. That's correct. If you look at the box, it represents about half of the data between 23 up to 30. So we have also another example here, gallons of fuels wasted per year. So we have now here 5, so 10, 15, 20, 25, 30, 35, 40. By the way, in real application, the interval would be depending on your choice. No? That is actually convenient to your choice. So the left whisker represents about 1/4 of the data. So about 25% of the data entries are less than 23. The right whisker represents about 1/4 of the data. So about 25% of the data entries are greater than 30. Also, the length of the left whisker is much longer than the right one. This indicates that the data set has a possible outlier to the left. So that's what you are going to consider. Once it's actually a longer one and it's in the left side, then there is a possibility of having an outlier. That is, the outlier is having a small value in comparison to the majority of the data. However, if the whisker is actually quite long, starting from Q3 going to the right side up to the maximum value, then we call also that's having a possibility of an outlier. That's actually an outlier in the perspective of having a big value in comparison to the majority of the data. So take note about this. Then we go to percentiles and other fractiles. So we look at quartiles, divide data into 4 equal parts. So Q1, Q2, and then Q3. Then deciles, divide data into 10 equal parts. So D1, D2, D3, so forth and so on up to D9. Then percentiles divide data into 100 equal parts. So P1, P2, P3 up to P99. The percentile is actually very common too, assessment of learning. No? It is actually dividing the data into 100 equal parts. And most standardized exams are actually using the concept of percentiles. So interpreting percentiles. The OGIV, so we mentioned about OGIV last time in the frequency distribution table video. The OGIV represents the cumulative frequency distribution for SAT, that test scores of college-bound students in a recent year. What test score represents the 80th percentile rank? So we look at this one here, 400 up to what? 1,600. Then we have here the percentile rank. So we look at 80, the 80th percentile rank. And when we approximate, that's actually what? One over 1,200. So if you're going to divide this one, so 1,200, 1,400. So the approximation is 1,250. This means that 80% of the students had SAT score of 1,250 or maybe less than 200, 1,250. So if your scaling of the x-axis and the scaling of the y-axis are not proper, not according to the rule of scaling both axes, according to the principles of basic mathematics in graphing values, then you would not get the appropriate value found in the x-axis. Percentile corresponds to a specific data entry. So how do we calculate percentile? To find the percentile that corresponds to a specific data entry x, use the formula. Percentile of x is equal to number of data entries less than x divided by the total number of data entries then times 100. And then round to the nearest whole number. So we have here example. For the data set in the second example, find the percentile that corresponds to 34,000 US dollars. So recall that the tuition costs are in thousands of dollars. So $34,000 is the data entry 34. Begin by ordering the data. So we have 16, 18, 18, 23, 25, 27, 30, 33, 34, 34, 35, 35, 36, 40, 40, 41, 44, 45, 47, 49, 50, 51, 51, 52, and then 52. So you have there. For the data set in the second example, find the percentile that corresponds to 34,000. So it's here 34,000. 34,000. So it's actually in hundreds of, in thousands of dollars. So 34,000. So there are 8 data entries less than 34. So we have 1, 2, 3, 4, 5, 6, 7, 8. So less than 34. So number of data entries less than x. For number 34, 8. So 34, how many data are less than 34? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8. And the total number of data entries. So how many data? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So divided by 25 times 100. So that gives you 32. So the tuition cost of 34,000 US dollars correspond to the 32nd percentile. So this 32 means the 32nd percentile. So the tuition cost 34,000 is greater than 32% of the other tuition stuff. So take note. No? So assignment number one, I'm going to change 34. I'm going to change 34 to 35. So you're going to have there the percentile for 34,000. So find the percentile that corresponds to 35,000 US dollars. That's number one assignment. Find the percentile that corresponds to 35,000 US dollars. And then next, number two, find the percentile that corresponds to 36,000 US dollars. Find the percentile that corresponds to 36,000 US dollars. And then the next one, find the percentile that corresponds to 40,000 US dollars. That corresponds to 40,000 US dollars. And number four, find the percentile that corresponds to 50,000 US dollars. That corresponds to 50,000 US dollars. So you have four assignments, no? Number one, number two, number three, and number four. Then compute that one and then submit this assignment together with the assignment that I have under measures of variation. And follow the same deadline. No? There's a deadline in there, so follow the deadline. And then I mentioned about the Friday N302. I think I was not able to mention N302. The due date of that would be Friday of next week also when we meet face to face for our N302. So that's it. Then we go to finding the z-score. No? We have the standard score or the z-score. So the standard score or the z-score represents the number of standard deviations a given value x fall from the standard mean or mu. So we look at in the previous video about measures of central tendency, and I illustrated in there the graph of a normal distribution or a symmetric distribution or a bell-shaped distribution. And if you remember, we have three standard deviations going to the right and three standard deviations going to the left. So a total of six standard deviations. So in here, we have the z-score. So value, any given value minus the mean divided by the standard deviation. So we have x minus mu divided by sigma. What is mu again? Population mean, sigma population standard deviation. So find the z-score. The mean speed of vehicles along a stretch of highway is 56 miles per gallon per hour with a standard deviation of 4 miles per hour. You measure the speeds of three cars traveling along the stretch of highway as 62 miles per hour, 42 miles per hour, and 56 miles per hour. Find the z-score that corresponds to each speed. Assume the distribution of the speeds is approximately a bell shape, a normal distribution, or a symmetric distribution. So finding the z-score, so we have there x, so we have 62 miles per gallon. So we have 62 minus 56. Take note that the given 56 for the mean, standard deviation 4. So we have now 62 minus 56 divided by 4. So the z is 1.5. X is equal to 47. So 47 minus 56. This one is the population mean divided by the standard deviation 4. So negative 2.25. For 56 miles per gallon, so we have 56 minus 56 divided by 4, and that's equal to 0. That's any value in the set minus the population standard deviation divided by the standard deviation. So it's equal to 0. So 62 miles per hour is 1.5 standard deviations above the mean. So say 1.5, it's actually above the mean because we have 0 at the middle. And going to the right side, we have 1 standard deviation, 2 standard deviations, then 3 standard deviations. Going to the left side, we have 1 standard deviation, 2 standard deviations, then 3 standard deviations. And all of these are below the mean. And then, so 45 miles per hour is 2.25 standard deviations below the mean. And the 56 miles per hour is equal to the mean of the data set. 47 miles per hour is unusually slow because its speed corresponds to a z-score of negative 2.29. So comparing the z-score from different data sets, no, the table shows the mean heights and standard deviations for a population of men and a population of women. Compare the z-scores for a 6 foot tall man and a 6 foot tall woman. Assume the distributions of the heights are approximately bell-shaped. So here are the given. Men's height sa population mean 69.9, sigma is 3.0. Women's height, so we have mu 64.3, and then sigma is 2.6. So comparing the z-score from different data sets. So note that 6 feet is equal to 72 inches. So find the z-score for each height. So we have z is equal to x minus mu divided by sigma. So we have 72 minus 69.9 divided by 3.0. So we have 0.7. For 6 foot tall woman, so we have 72 minus 64.3 divided by 2.6. So that's approximately 3.0. So comparing the z-score from different data sets. So the z-score for the 6 foot tall man is within one standard deviation of the mean, 69.9 inches. This is among the typical heights for a man. The z-score for the 6 foot tall woman is about 3 standard deviations from the mean, 64.3. This is unusual height for a woman. So take note of this condition. From -1 to positive, now from -2 up to +2, usual scores. These are the usual scores. And from here, we have -3 to +3. That is unusual. And this in the red line, that's above or less than -3 and greater than +3, very unusual scores. So take note of that index or classification, from -2 to +2, usual scores. From -3 to +3, unusual scores. And those that belong to this red line segment, this red one is going to the right after +3 and going to the left after -3. They are referred to very unusual scores. So take note of those different things, no? When you are going to look at into comparison of the z-scores, no? Applying that one to different data sets. So this would be the end, no, of the statistical part or the mathematical part of Ed 302, no, assessment of learning. However, for Ed 303 research methods, there are still other statistical tools classified as part of the descriptive statistics. Okay, so thank you very much.